Hello and welcome to the video. Today I'm going to be doing some Calc II midterm problems. So obviously the problems for Calc II midterm are not going to be the same everywhere. It's going to vary a bit place to place, like what is covered on the midterm, what types of problems, but this should give a general overview and just some practice for what you'll expect to see on your Calc II midterm. So let's get into it. So first we have the integral of 3x squared plus 6x minus 21 over x cubed minus 4x squared plus x minus 4 dx. So when you have an integral like this with a rational function that you don't know how to integrate by itself, you want to use partial fraction decomposition. So the first thing we need to do is we need to check, before we do anything else, the degree of the numerator and the degree of the denominator. So the degree of the numerator is 2, because our highest term is x squared. And for the denominator, it's 3. Now, if the degree of the numerator is equal to or greater than the degree of the denominator, then you need to use polynomial long division. But here, our degree is 2 on the top and 3 on the bottom, so we do not. Alright, so what we're going to do next, after we check that, is we want to factor the denominator. So we factor x cubed minus 4x squared plus x minus 4. Now, it might be a bit confusing how you factor this. If you have a cubic and you don't know, like, what to do next, generally for cubics, what you want to do is you want to treat this what you want in standard form, so from highest to lowest power, but then you want to factor this, these first two terms by itself. So to factor it fully, we take out an x squared to get x squared times x minus 4. For the second term, we just have a x minus 4, but you'll see in a minute, we're going to have a 1 there, because multiplying by 1 didn't change anything. So we're adding these things together. So if you notice, just by changing how we wrote it, it's an equivalent form, but we can see that this is going to factor as x squared plus 1 times x minus 4, because they both have that factor of x minus 4, and we can just pull that out. So that is fully factored. So x squared plus 1, that's an irreducible quadratic, and x minus 4 is a just linear term. So in its term for the partial fraction decomposition, this x squared plus 1, this is going to look like ax plus b over x squared plus 1. And the x minus 4 term, the linear term, is just going to be a constant over x squared plus 1. So the irreducible quadratic term is going to have a linear function of x over x squared plus 1. Meanwhile, the linear one is just going to have a constant. So now let's solve for a, b, and c. So the first thing that we're going to do is we're just going to write out what our what it's going to look like. So let's put in our factored version. Wait, I put x squared plus 1 over here. That was supposed to be x minus 4. I apologize. So that's equal to ax plus b over x squared plus 1 plus c over x minus 4. So we multiply both sides by this denominator. So what will happen is this ax plus b over x squared plus 1, that'll cancel with the x squared plus 1 and just leave us with ax plus b times x minus 4. And then the c term will cancel with the x minus 4 and just be c times x squared plus 1. So this will become 3x squared plus 6x minus 21 is equal to ax plus b times x minus 4 plus c times x squared plus 1. Alright, so now let's get rid of some of this so we can have room to solve. Alright, so once you have your equation to solve for a, b, and c, let's just remind ourselves that our rational function for our partial fraction decomposition, it's going to look like, we know it's going to look like ax plus b over x squared plus 1 plus c over x minus 4. So I'm just going to write that down so it doesn't get lost. So now let's solve for a, b, and c. So to solve for c, what we're going to do is we want this other term to go to 0, so we can just solve for c by itself. So we're going to sub in x equals 4. So we're going to substitute in 4 to everything, so to all the x's. So 4 squared is 16, plus 6 times 4 is 24, minus 21 is equal to, so this term is just going to go to 0 because it has a 4 minus 4, which is 0, so the whole thing will be going to 0 since it's multiplied by 0. And the other term with c will be c times 4 squared plus 1, so 17. So this is 3, and this is 48. So 48 plus 3 is 51. That's equal to 17c. So c is equal to 3 if we divide both sides by 17. All right, now we want to solve for a and b. So when you're solving for your coefficients for your term with the irreducible quadratic, so like your a and b in this example, you won't be able to find a 0 that will make the other stuff go to 0, if that makes sense. So here, this other term with c, we can't make that go to 0 because there's nothing we can substitute into that to make x squared plus 1 equal to 0. Instead, what you do is once you found all of your coefficients from the linear terms, here we only have one, you want to substitute in whatever those values are, and then you can solve for the constants for your irreducible quadratic term. So here we're going to leave the left side, so 3x squared plus 6x minus 21. Now let's expand out this. So this becomes ax squared minus 4ax plus bx minus 4b. And then c is equal to 3, so we're expand that out, we get plus 3x squared plus 3. All right, now we have 3x squared plus 6x minus 21 is equal to, now let's gather up all of our common terms with the x squareds, with the x's, with just the constant. So we can factor out an x squared from both ax squared and 3x squared. So this will become a plus 3x squared. And then for our x term, we have minus 4a and b. So plus minus 4a plus bx. And then for our constant term, things without any x's in it, is just minus 4b plus 3. So now what we're going to do is, because we have this equality, both sides are equal to each other, we can say that the coefficients for each, for the x squared, for the x, for the constant, all of those have to be equal to each other. So this means that 3 is equal to a plus 3. So a is equal to 0. So to solve for our b, we notice that negative 21 and minus 4b plus 3, those are both the constant terms. Those can be set equal to each other. So minus 21 is equal to minus 4b plus 3. So if we subtract 3 from both sides, we get minus 24 is equal to minus 4b. So b is equal to 6. So look at that. We've solved for our a, b, and our c. Or let me get rid of all of this. Okay, so now what we're going to do is we're just going to substitute that back in, and we can integrate. So we have our partial fraction decomposition. It's going to look like 0x plus b. So 0x is just 0, so we can ignore that. And then b is 6, and that's being divided by x squared plus 1. And then plus our c, which is 3 over x minus 4 dx. So now we've done our partial fraction decomposition, we can turn this integral into something more manageable. So now we can split this up. We can split this up into, well, let's factor out that 6 times the integral of 1 over x squared plus 1 dx plus 3 times the integral of 1 over x minus 4 dx. Okay. Alright, I can actually get rid of these now. Okay. So for this first term, this matches the integral for arctangent. So this is 3 squared plus 1 squared. This becomes just 6 times arctangent of x, because it's just a 1. You don't have to worry about it being a squared. So this is just 6 arctangent of x. Plus, for this one, it'll work out either way. Like, this is just 3 times the natural log of x minus 4, because that's in the denominator. But I want to show why. So, if you let u be x minus 4, du is just dx. So our differentials are the same. And this will become plus 3 times the integral of 1 over u du. Integral of 1 over u du, that's natural log of u. So plus 3 natural log u. And then that's just natural log of x minus 4. Okay. And then don't forget the plus c. So let me move this a little bit. And that is our final answer. Alright, so our next problem is to find the arc length of y equals 14x to the 3 halves on x's between 1 and 2. So, our formula for arc length is given by an integral. So, let me write that out. So, f prime, let me switch to a more bold. So, f prime of, or not f prime, the arc length on the integral from a to b is given by the integral from a to b of the square root of 1 plus f prime of x squared dx. So here, well, we're going to need to know our derivative. So what is the derivative of y equals 14x to the 3 halves? So what is y prime? Well, from our power, or, we can just pull out that 14. And then from our power rule, that 3 halves comes down. And then you multiply that by just the x to the power minus 1, so that'd be 1 half. So this becomes 14 over 2, that's 7 times 3, that's 21 square root x. Okay. Because 1 half power is square root. Okay. So for us, our a and b are 1 and 2. So this is the integral from 1 to 2 of the square root of 1 plus f prime of x squared. So you want to square 21 square root x. So, 21 squared, that is 441. X, because square root x squared just becomes x. dx. Alright, now what we can do is we can perform a u substitution. We can let u be 1 plus 441x. Now the reason I'm doing this is because I don't know how to integrate this function, but I know how to integrate the square root function. And I know that when we differentiate this x, it's just going to be some multiple of, when we find du, it's just going to be some multiple of dx. If it was like x squared, then our du would have an x term in it, which we don't have. But since it's just 441x, that'll differentiate to du equals 441 dx. And we can solve for dx by dividing by 441. And this works out quite nicely. So this becomes the integral from 1 to 2 of the square root of 1 plus 441x, that's u, times du over 441. So now I can pull out that 1 over 441. This is still from 1 to 2 of square root u du. So this becomes, alright, now we need to change our bounds. So our bounds will become, since u is 1 plus 441x, once we put this in terms of du, as soon as you change it to be in du, you need to change your bounds. So 1 plus 441 times 1, that's just 442. And then for the other one, it'd be 882 plus 1, so 883. Okay. So, I can just cross out those bounds. So, if we find the antiderivative of square root of u, that is, let's think about it. We do 1 over 1/2 plus 1, because that's 1/2 power, so 1 over 3/2. So that becomes 2/3, because it's the reciprocal. So 2/3 u to the 3/2, because 1/2 plus 1. And this is evaluated from 442 to 883. Alright, now I'm going to make a little bit of room. Alright. So we can pull out that 2/3. That becomes 2 over 441 times 3. That is, if I do that, 3 times 441. 1,323. And then we have u to the 3/2. So this would become 883 to the 3/2. Then we subtract off our lower bound. So upper bound minus lower bound. So 442 to the 3/2. And these are not perfect squares. So when you square root, it's going to be irrational. But that is our final answer. Alright, for this next problem, we want to find the area of a region bounded by two curves. So I find it useful to draw a sketch for these types of problems. So one of our functions is f of x equals negative 2x plus 4. So that'll look something like that. And our other function is g of x equals 2x squared. So that'll look something like this. So our region is going to be this. We want to find the area of that. So first things first, we want to find what are these intersection points. We'll do that. We set the two functions equal to each other. So 2x squared is equal to negative 2x plus 4. So if we add 2x and subtract 4 from both sides, we get 2x squared plus 2x minus 4 is equal to 0. I can divide everything here by 2, and I get x squared plus x minus 2 equals 0. So what multiplies negative 2 and adds to 1? Well, I think of negative 1 and 2. So this would become x minus 1 times x plus 2 is equal to 0. So x is going to be 1 and negative 2. So those are our intersection points. So this means that's just to find the bounds of our integral, pretty much. So that's going to be the bounds of our definite integral we set up. Now, we want to find which function do we subtract from the other. So what you do is you do the upper function, which here is this line, and you subtract off the lower function, which here is 2x squared. So for us, we're going to do minus 2x plus 4. Then we subtract off that lower function, so minus 2x squared dx. Alright, so now if I make a bit of room, fill that in. Okay, so this, if we put it in order from highest to lowest power, negative 2x squared minus 2x plus 4 dx. To make our algebra a little bit easier, I'm just going to factor out a 2. Actually, no, let's not. So if we use our power rule for integrals, this becomes negative 2 over 3, so you divide by the power plus 1, times x to the power plus 1, so x cubed. And then minus, so we're going to become an x squared, and then we divide everything by 2. So minus x squared, because 2 over 2 is just 1. Plus 4, and then we bring that up a power and divide by 1, which just leaves it the same. So that is our antiderivative. And our bounds are from negative 2 to 1. Alright, so the next step here is just to plug in our bounds. So if we plug in our upper bound, we get negative 2/3 1 cubed, that's just 1, minus 1 squared, that's just minus 1, plus 4. So this becomes, if I turn everything to, this will become negative 2/3 plus 3, and 3 is 9/3, which is just 7/3. So that's, we plug in our upper bound, plug in our lower bound, we get negative 2/3 times negative 2 cubed is negative 8, minus negative 2 squared, the whole thing squared. So the negative squared becomes a positive, so minus 4 plus 4 times negative 2 is negative 8. So this will become, those negatives will cancel out. We get 16 over 3 minus 12. Negative 12 is just negative 36 over 3. So this becomes negative 20 over 3. Now the next step is to subtract off our upper bound from our lower bound. So we do 7/3. That's what we got when we plugged in the upper bound. And we plugged in the lower bound, we got negative 20 over 3. So those are going to become a positive. This becomes 27 over 3, or just 9. And that is the final answer for that problem. Alright, up next we have an improper integral. So, the thing with improper integrals is usually you'll know how to integrate the integrands. That's not going to be the tricky part. It's going to be that your limits of, or your bounds of integration, usually one of them is going to be infinity, or there's another case I'm not going over in this video, but your function is undefined at one of your bounds. So for us, we have that one of our bounds is infinity. So the trick with that is instead of just finding the antiderivative, subtracting your upper bound from your lower bound, or subtracting your lower bound from your upper bound, what you do is you want to use a limit. So for us, you can use any letter. I'm going to use n. So become the limit is n goes to infinity of the integral from 2, and then replace that infinity with n, because you can subtract off an n when you're taking a limit, because it's not going to actually equal infinity, it's just getting closer and closer. So and then our integrand is 7 over x plus 4 to the 3/2 power dx. So what I'm going to do next is I'm going to pull out this 7. So it's going to become 7 times the limit as n goes to infinity of the integral from 2 to n of, I'm going to write x plus 4 to the 3/2 power. I'm going to write that as negative because it's in the denominator. So you can put it in the numerator and flip the sign. Now what I'm going to do is I'm going to perform a u substitution. So u is equal to x plus 4, because that's the thing on the inside. Find du, that's just dx. So now let's do this. So this is going to become 7 times the limit as n goes to infinity of the integral from 2 to n. And then we have u to the negative 3/2 du. Now, I just like to note, I forgot to change my bounds. So I gotta do that. So n plus 4, we don't have to change n because n is already going to infinity. So adding 4, it really doesn't change anything. But we do need to change our lower bounds because from x to u, we add 4 to x. So we go from x equals 2 to x equals 6, or u equals 6. So now this is our integral, and we're in the u world. So we can do now, we can find our antiderivative. So u to the negative 3/2 du, integrating that with respect to u, our antiderivative will be, we add 1 to the power, so that becomes u to the negative 1/2. And then we do 1 over negative 1/2, because 1 over the power plus 1, times u to the negative 1/2. And we're integrating that from 6, or we're evaluating that from 6 to n. Alright, so now let me clean this up a little bit. Alright. Now this let's pull out that negative 1/2, or that negative 2, because 1 over negative 1/2 is negative 2. So that's 7 times negative 2, that's negative 14. We can pull that out of the limit. Times the limit as n goes to infinity. U to the negative 1/2, I'm going to write that as 1 over square root u. And we're evaluating this from 6 to n. Now let's just plug in our n. So square root n So 1 over square root n minus 1 over square root 6. We plugged in our bounds of evaluation. Now, as n goes to infinity, we note the square root of square root of n is also going to go to infinity, but we're doing the reciprocal of that. We're doing 1 over square root of n. So 1 over something that's going to infinity is going to go to 0. So this is going to go to 0 as n goes to infinity. So we can just cross that guy out. Or we can evaluate it now. So this is going to become negative 14 times 0 minus 1 over square root 6. I'm going to write that as square root 6 over 6. This is negative 14 times negative square root 6 over 6. So these negatives will cancel. And this will become 14 over 6. It's the same thing as 7 over 3. And we have a square root 6. So 7 square root 6 over 3. That is the value of our improper integral. Alright, for this next integral, we're going to need integration by parts. Because if you notice, we're multiplying two functions of theta. And if we did u sub u equals 5 theta, then d theta would become, du would become just 5d theta, and we wouldn't have a theta term. So u sub would not work here. Instead, your hint is that two functions are being multiplied. Because of that, what we need to do is we need to set up our integration by parts. So let's have u be equal to theta. So that's the thing that we want to differentiate to, usually we want to differentiate to 1, or eventually differentiate to 0. And then we want this other stuff, everything else, to become dv. So dv is equal to cosine 5 theta d theta. So this becomes the integral of u dv. And from our integration by parts formula, this is u times v. So let me write that. u v ultraviolet voodoo. That's how I remember it. uv minus the integral of v du. Voodoo. That's kind of how I remember it. Okay. So now let's plug in our functions. So this tells us that this is the integral of u dv, and that's going to be equal to u, which is theta, times v. Now to get v, what we're going to do is we're going to integrate dv. So v is going to be the integral of cosine 5 theta d theta. So what this becomes is the integral of cosine sine. But then because we're multiplying by 5 on the inside, you do 1/5 on the outside. And we're not going to add a plus c because you do not, when you're doing this, I said the integral, the indefinite integral, but when you're integrating like that to find your v, you don't need to add a plus c. Alright, so v is going to be 1/5 sine of 5 theta. Now we need to find du, because that's also something we need for our formula. So du is, we just differentiate theta. So du is just 1 d theta. Don't forget the d theta. So this becomes theta times 1/5 sine of 5 theta minus the integral of v. So that's 1/5 sine 5 theta. And then d u is just d theta. So this becomes 1/5 theta sine of 5 theta minus 1/5 integral of sine of 5 theta d theta. So what is the integral of sine of 5 theta d theta? Well, we know the integral of sine is just minus cosine, because cosine differentiates to minus sine, so we do the opposite of that to differentiate to sine. So, since we have a 5 theta on the inside, we do a 1/5 on the outside. So this becomes 1/5 theta sine 5 theta minus 1/5, and then our antiderivative is negative 1/5 cosine of 5 theta. And now that all of our integrals are gone, we add our plus c. So these negatives cancel, make a positive. So we get 1/5 theta sine of 5 theta plus, and then 1/5 times 1/5 is 1/25 cosine of 5 theta plus c. And that is our final answer. Alright, so this next problem is a trig sub problem. So when you want to do a trig sub, you know that because you're going to have a square root with x squared minus something or plus something, or something minus x squared, there's going to be an x squared in a square root, and you're not able to use u sub. If you tried u sub, if you did u equals x squared minus 25, you would get du equals 2x dx. That's not what you want. So here what you do is trig sub. So this is the form of a secant substitution, because x squared minus 25. What you do is you identify this is 25, that's 5 squared. So you say, okay, we're going to let x be 5 secant of theta. Now what's dx? Dx is 5 times, what's the derivative of secant? That's tangent theta secant theta d theta. Now what is the square root of x squared minus 25? Let's find that part now. That is going to be the square root of 5 secant theta squared minus 25, which is square root of 25 secant squared theta minus 25. I can factor out 25 from everything, so this is square root of 25 secant squared theta minus 1. Well, from our Pythagorean identity, or one of our three, this is actually tangent squared theta. So this all becomes square root of 25 is 5, tangent theta, because the squared and the square root cancel. So that is what that part is. Now, the next part generally is going to be to draw your right triangle. So this is our angle theta. This is the opposite. This is the adjacent. This is the hypotenuse. Now, we have secant theta. We have x equals 5 secant theta. This means that secant theta is x over 5. But we also know that secant theta is 1 over cosine. And this is 1 over, we know that cosine is adjacent over hypotenuse. So we flip that, and this becomes hypotenuse over adjacent. So this is hypotenuse, and this is adjacent. So we know that our hypotenuse is going to have to be x. So let's just say hypotenuse equals x. Our adjacent is 5. How do we get our opposite? We do square root of x squared minus 5 squared. So that's square root of x squared minus 25 from our Pythagorean theorem. Alright, so now that's all of the kind of setup things that you need to do when you're doing trig sub. And now we can perform our trig sub. So this is going to become the integral of 5 we substitute x equals 5 secant theta. 5 secant theta whole thing cubed times, we know the square root is just 5 tangent theta, and then times our dx, which is times 5 tangent theta secant theta d theta. So this becomes the integral of, we have 5 to the third, we have 5 and another 5, so this is 5 to the fifth. Let's just pull that out. 5 to the fifth integral of, we have secant cubed, and then we have another secant over there, so secant to the fourth of theta times, let's see, we have a tangent there, another tangent there, tangent squared theta d theta. Now, when you have a secant to the to an even power, what you want to do is you want to pull out a secant squared. So this becomes 5 to the fifth power of secant squared theta tangent squared theta times secant squared theta d theta. Now what you want to do is you want to turn everything other than this part we set aside for secant squared. Other than that portion with the differential, what we want to do is we want to turn all the secants into tangents. And what we do is secant squared theta is tangent squared theta plus 1. So this is 5 to the fifth times the integral of tangent squared theta plus 1 tangent squared theta, and then times secant squared theta d theta. Now the reason why you do that when you have an even secant power where you set aside secant squared, the reason is this lets us do a u sub with u equals tangent theta. So let's get rid of some of this stuff just to make some room. We don't need that anymore. Alright, so we have this integral. Alright, so this is going to become 5 to the fifth power. Let's just leave that as is, 5 to the fifth for now. So we're going to do u sub with u equals tangent, u equals tangent theta, and then du is derivative tangent is secant squared theta d theta, and that's why we did that, because this becomes our du. So now let's substitute back in. So we have tangent squared, that's just u squared. We have a plus 1 times a u squared du. Now this is much more manageable. So this is 5 to the fifth times the integral of u to the fourth plus u squared du. This becomes 5 to the fifth times u to the fourth becomes 1/5 u to the fifth when we use our power rule for integrals, plus u squared becomes 1/3 u cubed. And then we have our plus c, because it's an indefinite integral. Cannot speak. Okay. So now let's use our definition for u. U is tangent theta. So this becomes 5 to the fifth times 1/5 tangent to the fifth theta plus 1/3 tangent to the third theta plus c. Alright, we need more room. Okay, so now what you do is we've kind of solved the integral in terms of theta, but we don't want the integral in terms of theta. We want it in terms of x, because that's what our original integral was in. So we're going to use some right triangle trigonometry to solve for tangent theta in terms of x. We know tangent is equal to opposite over adjacent. Well, for our theta, this is going to be square root of x squared minus 25 over our adjacent is 5. So this becomes 5 to the fifth times 1/5. Then we plug this in. X squared minus 25 over 5. Whole thing to the 5th power. Plus 1/3 tangent cubed. Or, I meant plug in our tangent. 1/3 square root of x squared minus 25 over 5. Whole thing cubed. And then we have our plus c. Now I'm thinking. Alright, yeah, we can leave it as is, but I'm going to do a bit of simplifications. Oh, wait, that's messy. Okay. So what I'm going to do is I'm going to first, this 5th power goes to both of these. So this is going to become 5 to the 5th power times 1 over, so we have a 1 over 5 to the 5th, and then we have another 5, so 1 over 5 to the 6th power times times x squared minus 25. We have a square root, and then we have a 5th power, so that's 5/2 power. Plus, this looks like 56, but that's 5 to the 6th. And then we have 1 over 3 times 5 to the 3rd power, because that 3/3 power goes both those, times times x squared minus 25 to the 3/2, because 3rd power in square root is 3/2 power, plus c. Alright, now we can distribute this 5 to the 5th power in both of these. This becomes 1 over 5, x squared minus 25 to the 5/2 power. And then we have a 5 to the 5th and 5 to the 3rd, so that'll leave a 5 squared on top, which is 25. So plus 25 over 3, x squared minus 25 to the 3/2 plus c. So that is our final answer. So trig subproblems are always a lot of work, but if you follow the steps correctly, they're generally pretty straightforward. Alright, our next problem is a solid revolution problem. So let's do it. So we're rotating the region bounded by y equals x squared and y equals 2x about the x-axis. And then we want to find the volume of that solid revolution produced when we do that. So let's make a little sketch. I find this to always be helpful. Y equals x squared looks like this. Y equals 2x looks like this. Okay, so this is y equals 2x, so y equals x squared. And then we're taking this region, and then we're rotating it about the x-axis. Alright, so first things first, let's find our bounds of integration. So to do that, similar to the problem earlier about area between curves, we set these two functions equal to each other. So x squared equals 2x. So x squared minus 2x equals 0. So x times x minus 2 equals 0. So our zeros are x equals 0 and 2. So this is 0. This is 2. Should probably use a different color. Okay. So now we can set up our integral. So it's from 0 to 2. Now, what method are we using? We have 3 methods. We have washer, shell, and disk. So we know it's not going to be a disk because our axis of rotation is the x-axis, and we're clearly not touching it over this whole interval from 0 to 2. But the washer method, where we have we have two different radiuses that we have to subtract from each other. That's what we're going to use, because if you notice, if we make one kind of like representative rectangle of our integral, it's going to look like that. So we're with respect to x. So this is going to be dx, and this is going to be our h. So if you notice, our rectangle is it's kind of, we're integrating perpendicular to the axis of rotation, which is the x-axis. So whenever you're integrating perpendicular to the axis of rotation, then you want to use the washer method. So the washer method, you do pi r squared, but for your different r's, you subtract them off. So pi times your outside r squared minus your inside r squared dx. So your outside r is the one farthest from your axis of rotation. So that's the integral from 0 to 2. And then let's pull out that pi. And then what's our outside r? That's going to be x. That's going to be 2x. Because that's farther from axis of rotation. So 2x, whole thing squared. And our inside r, the one that's closer, is x squared, whole thing squared, dx. So this becomes pi times the integral from 0 to 2 of, if we distribute this, this becomes x to the fourth negative plus 4x squared dx. So this is just a simple power rule. So pi times negative 1/5 x to the fifth plus 4/3 x cubed. And then from 0 to 2, because we bump the power up and divide by whatever that number is for both of them. So let's plug in, well, we know if we subtract off 0 from when we plug in 2, whenever we plug in 0, that's just going to give us 0 to the fifth and then 0 cubed, so this whole thing is going to be 0. But if we plug in 2, that's just going to be the whole expression for our answer. So negative 1/5 times 2 to the fifth, that's 32, plus 4/3, and then 2 cubed is 8. So this becomes pi times negative 32 over 5, plus 4 times 8 is 32 over 3. So this is pi times, let's see, let's multiply negative 32 over 5. Let's multiply top and bottom by 3. So that becomes negative 96 over 15 plus 32 whole thing times 5. That becomes 150 plus 10, so 160 over 15. So this becomes 64, let me think, 64 pi over 15. And that is our final answer. So let me write this over here. 64 pi over 15. Alright, so for our last problem, we have a trig sub problem. So for whatever trig function in your integral, well, for cosine and sine, this is different for tangent and secant. But for cosine and sine, whatever one, or if you have both, you could do either. It just depends on what works nicer. Whatever one has an odd power, that's the one that you want to set aside one. So for this example, or for this problem, we have cosine to the 28 of t. And then we're going to set aside a sine of t. So this will become sine squared of t times sine t. Times sine of t dt. Now the reason I did this is because if we let u be cosine of t, then du is minus sine t dt. So this means sine t dt is negative du. So we can just plug this thing and change this thing to du. And then all we have to do is change our signs to cosines, and then we can have this whole integral in terms of u. So this is going to become the integral of cosine of 28, that's just u to the 28, and then sine squared of t, that is 1 minus cosine squared of t, so that's 1 minus u squared, because u is cosine. And then this is, this is negative du. Should have said that. This is negative du, as we saw earlier. So this is negative integral of, if we distribute this out, that's, actually, how about I just use this negative to flip this order around. So this is going to become u to the 28 times u squared minus 1. So that is, if we distribute that out, that's u to the 30 minus u to the 28 du. So that's, if we use our power rule, we add 1 to the power and divide by that, multiply by the power, by u to the power plus 1. We do the same thing for the other one. So 1 over 29 u to the 29. And then we add our plus c, because we have an indefinite integral. Now, let's substitute back in u equals cosine t. So this becomes 1 over 31 cosine to the 31 of t minus 1 over 29 cosine to the 29 of t plus c. Alright, that is our final answer. Alright, thank you for watching. I wish you luck on your Calc II midterm, if that is what you're studying for. And I hope that you have a good rest of your day. Bye-bye.